What we will talk about are state trees and AI in general. I have to say I have tricked you here a little bit because it's gonna be mostly about AI in general and very little about state tree on the end. The idea here is to understand how AI in games usually works, how we think about designing AI, and then we happen to talk about state trees because state trees is a default way how to make AI in Unreal. So why should you listen to me? Mainly because I have done a lot of implementations of AI. I have been working with Unreal for 7 to 8 years at this point, and during the time I have been working on many projects that I have been responsible for both architecting the AI as well as implementing the individual agents. So, I have a project that I have created and I will be going through it later. You can download it. I put it on GitHub already. You can use it later for reference as well. It's gonna stay up there. But if you wanna download it already, you can do so right away. So you can go through it with me later. Right. What AI in games is? AI here we use as a shortcut for artificial intelligence. And to answer what AI is, we can first try to understand how it works. And we're gonna do another reversal to understand how it usually works. Let's understand what it is not. And the first important thing that we now have to add as a distinction is that it's not LLMs. It's not large language models, which these days is marketed as AI. I'm talking about things like ChatGPT, Cloud, these sort of chatbots. That's completely different from how AI in games works. So, cool. And another cool thing is that it's not magic either. It may seem complicated whenever you see some complicated system. It may looks like something that you cannot understand, but you have to realize that it's just a complex system. And as any complex system, it's just something that's built from a lot of really simple systems. So this should be actually quite encouraging because it means you can really learn anything, not just how AI works, but anything. As long as you manage to break it down into individual parts, you can understand those small individual systems, how they put together into a one complex system. So the easiest way how we can define AI is as a reactive algorithm. It's something that reacts in some way to our input. Arguably, this could be used for almost any algorithm, but let's keep it simple for us. Usually, we think about this as a AI agent, some sort of an enemy or perhaps friendly NPC that runs around in the world, and we can interact with it in some way, and it interacts to what we do. Perhaps if we move to its range, it's gonna start attack us. If we run away from it, it will potentially hide. A good thing to realize is that it doesn't necessarily have to be a humanoid. It doesn't necessarily have to be a NPC or something that's just moving around. The environment can be AI in game quite well, actually. You can think about this as a lot of, especially horror games, tend to have the environment and the world around you responding to your actions. If you tend to hide a lot, it will give you less spaces to hide. And all of this can very easily fall under AI, because it in some ways reacts to our players' reactions. So, let's look at some common approaches to AI. And when I say common approaches, what I really mean, how do we think about architecture of AI? How can we architect and design AI to behave the way we want it? There are three most important ones that we really care about, and the primary one is something called the decision tree. In Unreal, the primary method, how it used to be implemented, was behavior trees. We'll get to them in a bit. How we can think about this is that we have a state, and those states happen sequentially, one after another. We can look at some practical examples. This is exactly from behavior trees, and we can see here that we have three sort of options that this AI can do. We have here some selector, so something that's deciding what the AI does, and depending on some condition, it will go either here, here, or there. Our condition here is quite clearly stated as line of sight. So does our AI see the player? If so, it's gonna go into our state of chasing the player. And here we will execute few actions, one after another, sequentially. So we can rotate towards it, chase him, chasing means moving to location. This is a bit of a nonsense we don't care about here, but important is that they are executed one after another. Then, if this condition side of the player is false, we will switch into patrolling, or we will go to patrolling. We don't necessarily have to go through this state at all. And it's gonna find us some location, move to it, and then wait. And then you can think about writing AI within this architecture, within these decision trees, as huge trees with many potential branches and many potential routes that allow us to create quite complicated behavior based on a bunch of conditions like this one. Now, a lot more common these days approach is a stats-based oriented, so stats is shortcut for statistics, and that's when the actions and reactions of our AI are changing based on some hidden metrics. And to demonstrate how hidden those metrics are, I'm gonna use the example of a game where the metrics aren't hidden at all. So this is, of course, The Sims. The Sims, funnily enough, works actually as a really good example how to imagine how statistic-based approach can work. As we can see here, we have our character, our Sims, and our Sims has a certain metrics. We have here some hunger metric, some energy metric, and perhaps social metric. And over the day of the Sims, over the time the Sim is active, we will see those metrics changing. So the hunger will slowly go lower and the energy goes slowly lower, etc., etc. And depending on the state, the value of these metrics, this sim will do different actions. If its hunger is very low, it will have to go eat food. If its energy is very low, it will have to go to sleep. And in the exact same way, when we are architecting our AI to be based on metrics, it will take these values in, I suppose, it will decide based on them and do those actions. So if the AI sees that its hunger is very low, it will go eat. If it sees its energy is low, it will go to sleep. You can very often see this approach when the AI in games is set up rather as a ecosystem. It's something that we want to give player the impression that the world exists outside of him. Even if the player wasn't there, the world would still exist. Usually there is some day and night cycle involved. And metrics is something that helps us with this a lot. Then we have a last approach that's arguably least common, and for a good reason, but still quite useful, and it's probably becoming more and more common. There is one exception where this approach is actually the most common, and I'm gonna get to it in a bit. How it works is that we specify a goal, and then the AI has a list of available actions, and it will pick those actions depending on what's the best way to achieve that goal. We don't tell it, we basically set up a system that will let us do it. There's a graph that lets us quite nicely describe that. So we have here some world, don't care about that, we have here planner. Planner is our primary decision maker. You can think about it as a brain of the AI. We will give our AI some goal. Perhaps the goal can be attack the player, and then it will figure out which action should go in which order and then execute it. We don't tell it which action should go when. It will have to decide it based on how we programmed this planner. The action here can be, for example, move somewhere, find actor, and can be attack, it can be run away. So we'll have to figure out which order should they go in, how long we should stay in there, and all that. Then, of course, it will tell to our agent, our actual thing. We can think about it as a brain deciding on the body what the body should do. This approach is usually by far the most fun to program. Nevertheless, it's rarely the one that ends up being the most fun for the player. This is a bit of a trick a lot of programmers can fall into, that they end up doing and architecting their system for the game in a way that makes it most fun for them, but not necessarily brings most value to the players themselves. Realistically, when you are seeing the game and you play the game and engage with it as a player, you can't really tell whether the AI that's right in front of you, throwing a grenade or you or whatever it's doing to threaten your life, is done with a goal-oriented system or state-based, or maybe there's some statistics. You don't care at all. What you as a player care about is whether it is fun or not. And usually you can get to equally fun, I suppose, factor with a state-based system, and it's a lot easier to set up. So we in games usually end up with state-based system instead of goal-oriented. There is an exception though, and that exception is robotics. We have done some works with robotics, and the goal-oriented approach is exactly the only one that really makes sense there. The reason why that is because you don't have complete control over your environment. In virtual worlds, when you are in the Unreal or whatnot, you always have 100% control of everything that's happening. Whenever you tell your AI to pick up a plate, any object, you know exactly what rotation it has, where it is, you know how big it is, and all that. You don't really know that in a real world. You have to have a deciding actions that will let you evaluate that and then execute it based on evaluation of those actions. For the practical example could be a real life robot needs to figure out, okay, how big is the plate, how is it rotated. Well, the plate usually doesn't have to be rotated, but that's beside the point. Whatever object it's picking up, it needs to have a certain rotation, and we can't predict that. Maybe someone walked over and slightly touched on it or moved it around, and the robot will have to always know that very accurately. And we don't know that, so we need to always decide it per action, which is where our goal-oriented approach really shines. Right. Let's look at what all these common approaches have in common and what is kind of true for all of them. And the primary thing is that they are almost all the same under the hood. If you actually look at the code that's being executed, the actual suppose programs that are put there, they are almost the same. The point of why we think about these, or why I would like you to think about these as a separate approaches, is because they help you think about your AI. They are here really for us humans to design and plan our AI a lot more accurately. State trees and behavior trees, which are the systems that we use for our AI, help us keep it all organized. They are there just for us, helps us design, helps us organize. That's what we care about there. Important thing is they all overlap. They are not a separate categories that never ever have anything in common. They are almost always you are in your individual AI, you are almost always have an aspect of both of them. A typical example of how your state approach and metrics approach will work is, for example, your health. A typical example of using a state would be your AI is either in the attacking mode when it's rushing the player, and then it's running away and rushing the player again. And anytime it finishes this action, finishes rush at the player, it will evaluate how much health it has left. If the health is below certain threshold, let's say it has less than 20% or something, then it can run away further and try to drink a potion. This is just an obvious example of how you are going to use some hidden metric. Potentially not hidden, but let's think about them as hidden metric to adjust its behavior. You are very rarely in a situation where you have 100% states and 100% metrics. Let's do a step back to machine learning. Machine learning is a technology that's responsible for large language models as well. And machine learning is starting to show up in games a bit more. To be clear, machine learning is used a lot in actual games. It's used in actual games quite a lot. Rarely in AI though. There's a lot of in upscaling and in rendering, but that's not quite what we are talking about today. How you can think about machine learning is that they are algorithms that help you predict and learn players' behavior. As you can imagine, that can be very useful for games because you will want to adjust the fun for the player based on his reactions. So The typical example can be from stealth games or more tactical games, maybe something like Metal Gear Solid 5. Games like this tend to adjust enemies and AI based on the player's reaction. For example, if the player shoots headshots all the time, then the enemy starts wearing helmets and the headshots are not so effective anymore. Another example can be if a player often shoots with a rocket launcher, then the enemies stop being on one place, they start separating and they start rushing the player, so the rockets from a rocket launcher aren't that effective. You don't really need machine learning algorithms for something like this. Nevertheless, you can apply a lot of the principles of it, and perhaps there are cases where you can use the actual machine learning algorithms. Right. So now we have some understanding of how AI can be done generally. So far, we have been mostly platform agnostic. So let's look at what can be actually done in Unreal. And the secret is that it's all of it. All of it can be easily done in any engine. We're gonna talk now about specifically which things can be done in what would you use for separate approaches in Unreal, but I would urge you to think about these as ideas to help you organize in your mind how your AI works, instead of this is the tool, this is the program I have to use to make AI. That tends to be a very poor way to think about it. You should be really thinking about yourself as someone that accomplishes the outcome in the game, not someone that knows a specific tool. Right. So, Unreal Engine, we start with something obvious, and that's just something I call pure implementation. And it means either blueprints or C++. I really hope blueprints, because doing AI in C++ like this would be a bit of a hellish thing to do through. And that's simply because we have a very easy and obvious visual debugger. We can at any point see exactly where our code is. So this is quite simple example. We have here a state, we have here state on player spotted, and then we have a state on follow the player. When we finish our on player scene, we're gonna jump into follow player and we're gonna move towards the player. Pretty straightforward. You can get really far in making your AI quite impressive just with pure blueprints. Doesn't mean you should do that, but you can do that. We have a old approach that at this point I treat as deprecated, but it's something we have covered already. It's behavior trees. That used to be how we used to organize AI. Then our newest approach is StateTrees, which is a modern replacement, and Epic has stated quite clearly that this is what will be replacing and used for all AI in the future. So this is an example how our state tree works. I'm gonna go into a specific example in Engine in a bit, but let's have just a quick overview of what is happening here, because that can help us kind of understand what it will be like. So we can see here that we have two main states. We have our state in danger and a state when it's peaceful. We can think about this sort of a behavior being of something like a deer, perhaps some small animal, anything like that. And what we can see here is that whenever our deer is in danger state, it will go into one of these substates. Either it's gonna flee, probably best for it, then it can try to wait and assess the situation, and then it can watch the threat. And whenever it finishes one of these states, it's gonna go back to our main state and potentially switch to a different one. Or it can transition into our peaceful state. That's presumably where the danger is very far, and then it will go into one of these substates once again. We can go into our wander state, which means it's gonna go to a random location, and when it finishes the moving to random location, it's gonna graze. It means it's gonna eat some grass. If it will fail, it will go back peacefully and probably wander around again. So we do have one exception, and that exception is crowds. The reason why we don't really why we treat crowds as an exception is because of performance, really. Generally, I would urge you against thinking about AI as your performance bottleneck. In most modern games, programming is very unlikely to be the cause of performance hits on your game, unless you are doing something really stupid, and then the problem really isn't the programming, that's the problem is that you are doing something stupid. So the issue I'm talking about here is the crowds is that we are not gonna be able to run a individual behavior programs for hundreds or thousands of characters in the actual game. So if you can imagine that you have 1,000 or maybe even 100 is quite a bit already characters, the 100 zombies that are running at you at the same time, you will not be able to run the AI at a good frame rate, at a good speed for each of them individually. So what we do is to start controlling them in the chunks. You can either control all of them at once, means you have one capital controller that's just controlling each of these individual characters, each of these individual entities that are running at the player. More likely you will separate them into chunks. Let's say you have 100 of them, you got one here that's 50, then another one that's 30 of them, and then maybe one more that's 20. Usually you would want to separate it because you will want some variety. It tends to be really easy to avoid a crowd that just runs all of them at you at the same time. It gets a bit more difficult when 20 people split and start going behind you. So quite a good idea to start to treat them in chunks. How we can do something like this, we have two potential ways that are probably the most useful, and that's mass entity, which is basically Unreal's ECS system. In case you're not familiar with ECS, it's a shortcut for entity component system. How you can think about it is a fundamentally different architecture from object-oriented programming, which is what you are normally used to when you work with Unreal, right? We have some parent, we have some properties that are inherited, and we have some children that have those properties. ECS works very differently. You can think about them as having a lot of different objects, and we can assign by some controller those objects a specific properties. And that property can be move left or move right, but it has only that property. It doesn't have anything else. This software architecture allows for quite a lot of entities, a lot of objects to exist at the same time at very minimal cost. Another approach to achieve the same thing is actually Niagara. It's particle effects. And when you think about it, particle effects are exactly the same approach. We have a bunch of objects, instanced objects usually, and we tell them what to do. Which exactly leads me to my second statement, which is Niagara is basically ECS but run on GPU. So we have covered now how we usually use what we usually use in Unreal. And like I mentioned, I consider StateTrees, and at this point probably anyone should consider StateTrees as a go-to solution for Unreal. So why is that? One of the best things for them is that we have a really easy way to access all the variables. And the individual state tree and individual states that you have within that state tree have a full access to the actor. You don't need anything like a blackboard or any interfaces or any weird way to transfer the values and the data from one actor to the state tree. You have access to all of them right from the start. Your state tree has a full context of the actor you are working with. I will demonstrate all of this practically in the example once we get into Unreal in a bit. They have universal actions. By action, I mean here things like move to location, pick up something, attack, whoever. These things can be universal. They don't have to be written to any specific actor. They can be easily used between different state trees and between different states, even within the same state tree. A huge benefit, that's the main argument why it should replace behavior trees for you, is that you can swap the state trees in the runtime. Usually how it used to be is if you wanted to have a variety of behavior within the same actor, is that you had to build these huge trees that would have all these possible behaviors. You can think about it as, let's say you have 3 different behaviors that the same actor can potentially exhibit. It can be a fearful behavior, it can be aggressive behavior, and maybe kind behavior. A little bit of a weird AI to have a kind behavior, but let's assume so. Maybe it's a PC. So If you had to do that with behavior trees or hard-coded with blueprints, you would have to have all of these possibilities at once. Not with state trees. State trees can have all of these behaviors separately. There can be state tree for aggressive behavior, state tree for fearful behavior, and you can switch them in runtime. This has a huge benefit because it allows you to keep your code pretty small. You can keep in individual state tree only the code and only the options that's relevant to that specific state tree. Alright, another very cool thing about state trees is that they are actually not just for AI. They are a universal state-based system. So anything that's using states, state tree can be used for. Example could be quests, for example, or missions. So if you have a quest that has multiple stages, that's basically states. Stage and state here are practically the same thing. You can use, you can set up a state tree to track your quest. You can use it for animations. Perhaps you don't want to use an animation blueprint. Maybe you are not working with a skeletal mesh. And a state tree can be perfectly valid for you to use as a animation replacement, as an animation blueprint replacement. Can be really useful for combos. You can think about it as you are doing one combo, second combo, and one attack and second attack, and those attacks should chain on each other in different ways. We can think about Mortal Kombat or these kind of 2D fighting games as obvious examples, but combos often show up in RPGs and in any RPG-like games. So something that really easy, it would be very easy to implement something like that with state trees. Environment states. Perhaps we may want to have something like a window, and that window can exist in many different states and forms. We can have a window that's closed, we can have a window that's open, it's half open, and perhaps 3/4 open. I don't know what you do with your windows. These all can be tracked within the state trees. It can be quite useful to handle that instead of having a complicated enumeration. And what's more important is that it can have different behavior depending on which state it is in. Again, this whole state tree system is here to help you keep your code organized. That's how you think about it. It's just a container to make things easier for you. Right. Skills and level progression, of course. If you think about like Skyrim or any RPG, anything that has a dedicated skills that have their own state within which they progress, depending on your level, that specific skill should act probably differently. State tree allows you to handle this really easily. Simply anything that has a multiple states. Let's look at a practical example then. So I would like to start with a pure blueprints example. So I have here my blueprints AI, and I have here something that you have, if you have worked with AI, you probably set up something very similar. I have here 3 zombies, I have here my AI base, and I have 3 variations of this AI. If I simulate my game, I'm gonna see here 3 different sort of AIs. Each of them have very similar behavior with some variety between them. So first, let's look at how the AI looks by itself. So we're gonna have here a dedicated AI graph just to keep it nicely organized, and we can see that we have here really just about 3 different states. We have here a wandering state, we have here on C player state, and we have here an attack state that's not commented, which is stupid, but let's ignore that. So let's look at our wandering state. The code is quite straightforward. We're gonna find ourselves a random location, we're gonna move there, and then we're gonna wander again. That's it. When we see our player, we will check who we are seeing, and then we are gonna attack the player. Then our attacking player simply leads to moving towards the player and playing a animation, and then checking if we detected anything. That's everything this AI does. For simple logic like this, a blueprint implementation tends to probably be the best. I'm mainly showing you this so you can see example of pure blueprints and how the exact same way will be implemented in state trees. So we got this. And let's look at some variety, because as you notice here, I didn't really adjust any variety. And if I actually open my blueprints, you will see that there is nothing changed here. The blueprints are exactly the same. If I open my crawler, I didn't change anything except few adjustments in the viewport, which is just changing the scale. Our sprinter is the only exception because I wanted to give him a random speed. If I didn't want to give him a random speed, I would just adjust it here in the character movement. So how this is accomplished is that we set up by default in our AI base some variables. We have here some animations, properties that we can adjust, variables. And those are then changed inside the individual actors. This would be a very typical approach when you are using a traditional object-oriented programming. You have here a parent that has all the common functionality of all these actors of the same class, of the same character, and then have and adjust the things that you know you will want to adjust per children in separate variables. So our example here is of course our walk animation. So we have here a random variety of animations. So that means whenever this AI spawns, it will randomly pick one of these animations. We have here a attack montage. So what animation should it play when it's attacking? Attack radius, how close should it be when it's attacking? And of course our idle animation, what it should do when it's just hanging around and player went off, turned off game or whatnot. Right. And if we actually see the game, we can see it's quite straightforward. Just with adjusting the few variables, we have gotten a lot of variety in how our enemies behave. Code was quite straightforward. I don't have here a player to quite demonstrate it, but you hopefully get the idea. So this is how you would set up very simple setting with pure blueprints. So let's look at state tree. State tree, we can look at our actor first, perhaps. We have our AI state tree. It inherits from the AI base as well, but it doesn't use any of its logic. It's disabled. It's just there for context. So our AI state tree doesn't need any of these things implemented. It's simply handled in our state tree. You can add our state tree as a separate component. In case you don't have it enabled, you need to have state tree as a plugin. Since I don't know which version, 4 or 3, 5.3 or 5.4, it's enabled by default, but if you don't have it here to add, you can just open it there. And we're gonna see here the exact same thing. We have here our representation of our state tree, which is our basic enemy. I created just one, but the other would be exactly the same. There's just not much to change. This can be changed in runtime, like I mentioned before. And again, we have here a few parameters that we could adjust and modify it. We could again adjust it even without opening the actual blueprint. We are gonna get rid of these characters and drop our state tree AI in here. We will see that it does the exact same thing. It moves from random location to random location. It's gonna wait, drink a coffee or whatnot, and then attack the player in case it sees him. So to see the actual implementation, let's open our state tree. And as you can see, it's almost identical to what we have seen in our blueprints. So we have here two main states. Our state is wandering around and our state is chasing the player. While it's wandering around, it will move to some random location. We can see we have a task. Task also has some parameters. And once it finishes wandering, it will go to wait. Once it finishes waiting, it will go back to wandering and just loop in between those until something transitions it from wandering into a chasing the player. Once we actually enter chasing the player, we have here a little bit more of a variety. We start by chasing the player, which we will see is just move to player, individual task that has some parameters. And when it finishes, it reaches the player, we will transition into attack. Our attack has a task, which is a attack player, and whenever it finishes it, it will go either, if it succeeded, it will attack again. We can nicely see it visualized here. If it's gonna fail, it will go into chasing, because it couldn't reach the player, it means it needs to reach it again. We do see here some parameters that we can adjust here. If you worked with Niagara or with materials, this is the exact same logic. We can set up here a few parameters. Here it's called property for some stupid reason. Should just call it variable. And here we can modify these things. So what I mentioned before is that we have a full access to our context actor. And when you create the state tree, I'm gonna click on your schema and decide which state tree, which actor does it have context of. That means which variables does it can it access. So that allows us to easily connect things connected to any of the variables. So let's say that in our move to player, I want to grab my running speed. I want it to be taken from some of my parameters inside the game. So I can look at my character movement, and perhaps I want to link it with my max walk speed. Because this is of course a character that's inherited from a character class, so I can just grab that parameter and connect it. I don't need to even make here a walk speed. I can just use the one from character movement or any other new variable that I would create inside this class. Okay. With that, let's look at the actual individual tasks. They exist as a separate actors, separate as well. We can call it separate blueprints, and they can be used on any of these. I would like to really show them to you one by one, because that allow one by one in comparison with our base, because that allows us to really see that there is very little different except the way they are organized. So let's start with move to random location. So we get our move to random location in our state tree, which is that's AI's finds random location. We get some checks that we don't have in our original. Doesn't matter. This is not really relevant. And then moves to location. If it succeeds, it finishes the task successfully. If it failed the task. In the exact same way we see here, find a random location. Don't do the check. Go to that location. All right. Let's before we progress to more actions, let's look at a bit of a overview how our task works. It's quite straightforward. We have here about 4 functions that matter. Really, only 2 of them matters, but it's good to be aware of them. And that's our enter state, our exit state, and perhaps our tick. Exit state you are not that likely to use, but perhaps you will want to handle something on transition. So on our enter state, that's basically our begin play. When in our state 3, we enter this chase state. We enter this chase state. Oh, come on. Enter this state chase. We have our move to play. I'm going to actually do the attacking. Wait, which one are we looking at? We're looking at the wandering. There we go. Whenever we enter our move to random location task, we are going to trigger our event enter state. So here we execute whatever logic we want. Pretty straightforward. Now, what makes this useful is because now I can just grab this task and add it to something else. So perhaps after it finishes attacking, if it attacked failed, maybe I want it to go into a random location instead of going back into chasing. I could of course route it back here in the wandering, but perhaps I don't want to combine my chasing state with my wandering state. So what I can do is to add here a simple new state, which is gonna let me go wander around. And in my wander around, I'm simply gonna add a task, and the task is gonna be move to random location. I'm gonna connect here my parameters. By default, it of course doesn't know what variables I want to work with, so I will tell it. So it should work with my actor, because my context actor is the one this state tree is assigned to. In our case, our not AI base, but the state base that we set up here. We can connect it with a radius, and we can connect it with our walking speed. Where are we? Parameters, there we go. Walking speed. So now I'm gonna simply change it without much of a fuss to go into wander around. So now after it fails the attack, it will go into wander around instead of trying to chase again. As you can see, easily I reuse the task that I created for something here. This is almost as practical as function libraries. It's just a continuous states. In the exact same way, we have our move to player, which is simply on entering the state, AI move to our target location, which is our player, and make sure we know what actors moves. If it succeeds, finish successful. If it fails, fail successfully, I suppose. If we do have here the exact same thing on our AI attack the player, we move to location, and then we attack it. Here we have combined AI move to and play montage. In the state tree, I have it separately. The primary reason is because tasks in state trees are so universal, they can be so easily reused. It just makes more sense to keep them in separate code. So you are more likely to have them as a modular code that you can take them out and put them on any specific location. That's our move to player. Let's look at the last one. state action attacking, and that's simply our playing the montage. Then when it finishes playing, we succeed. If it was interrupted, perhaps player attacked it while it was attacking, and it will fail. And if and during it, I want to on some notify, know whether I hit the player or not. Again, the exact same thing that we are doing here. The code is identical. Cool, let's get our state tree. That's pretty much how the state trees work. Let's jump back into the presentation. Right, state tree example, blueprints example, and with this, now we have some understanding of what our how they work practically, how we architect them. So let's try to think about when should we use what. And our first question is, when should we use state trees? And the answer is most of the times. In majority of the cases, state trees are, and from what Epic is communicating to us, the default way to set up AI, and much more than AI, as we have already covered. In most cases, you should go with state trees. There are cases, though, where pure implementation using blueprints or C++ may make more sense. The case can be, for example, if AI is really simple. If it's really supposed to be just stand around, attack the player when he sees you, setting up state tree is kind of cumbersome. It doesn't really help you that much. It slows you down because takes a little bit longer to set up. You get some performance boost using state trees, but like I mentioned, performance shouldn't really be your consideration with something like this. You are a lot more likely to shoot yourself in the foot with your art assets or doing a lot of other stupid stuff. Your decision between state trees, behavior trees, or pure implementation is close to impossible to really impact your frame rate in any significant manner. Like I mentioned, if it's really simple, makes sense. You may be in a situation where your AI requirements, the way the AI should behave, is very unusual. Maybe your AI doesn't work with states. Perhaps everything should be happening simultaneously. It would be very strange AI, very different to how majority of the games work, but perhaps you will work on a game where that is the case. In such case, it may make sense to create your own AI system. Perhaps you write some backend in C++, you create your own editor utility, so you have some nice UI for that as well. It happens quite often if you work in bigger teams. And then AI state trees or blueprints would just kind of, state trees or behavior trees would kind of complicate it for you and hurt you more than they would help you. Again, I think you are very unlikely to be in that situation, but it's not impossible. The last example is, of course, prototyping. If you are quite sure or reasonably certain that 80 to 90% of your code will be thrown away, then it doesn't make much sense to spend time creating state trees, because it's gonna be nice and pretty, but you're gonna throw it away anyway, so it doesn't matter, it was nice and pretty. For prototyping, using pure blueprints makes usually a lot more sense. Right. Of course, our last offender is behavior trees, and to the question when you should behavior trees, I think it's rather straightforward. At this point, I would very strongly suggest against it in any fashion.